All right. Let's start the switch problem now. So we're given a sequential switching circuit, so you can already know that there's going to be a lot of work involved in this. This is the circuit we are given. We are told that switch A was closed and switch B was open for a long time at t equals 0. Before t equals 0. Then at t equals 0, switch A is open, and then at t equals 2.1 second, switch B is closed. Find the voltage VCT at t equals 3 seconds. So I'm going to try something new here, so bear with me. I'm going to work backwards so we can understand what the question's asking for and what we need to be able to solve for it. So we know that at 2.1 or at 3 seconds, there's been two switching events that have occurred. Switch A has opened and switch B has closed. So we know that this is going to be our equation. VC at 2.1 minus VC of infinity e to the negative t minus 2.1 over tau. And this is for t greater than 2.1, right? We know using this equation, we can plug in 3 seconds and solve for VC at t equals 3, and we can get the answer that the question is looking for. However, in order to do that, we're going to need to find our initial condition, VC of 2.1. In order to do that, we are going to have to build this equation. VC of infinity e to the negative t over tau. This time frame.
So in general, for switching questions, are you always trying to step?
If there's multiple switching events. So at t equals 0, there's a switching event, and at t equals 2.1, there's a switching event. So you know you're going to need two separate equations for each one. And we're going to use this first equation to solve for VC of 2.1. So let's go ahead and get started, and let's look for VC of 0, right? When the circuit is in steady state and switch A is closed and switch B is open. So we're going to draw that circuit with switch A closed and B open.
With the second equation, would it be t smaller than 4.1?
It actually would be inclusive because it's the voltage across a capacitor. So it doesn't change instantaneously. So it's going to be equal for both bounds. Right, and this voltage across our capacitor, drawn as an open circuit because it's in steady state, is VC of 0. And switch B at this point is open, right? So we can get rid of this entire half of the circuit because it's an open circuit loop. It doesn't affect anything. So the first step is to solve for VC of 0.
Why is VC 0 open?
Because the capacitor is in steady state, and when capacitors are in steady state, we draw them as open circuits. And the question specifically says that these switches have been in the position that they are in for a long time. That, if it doesn't say that, you can't assume it to be in steady state, but since it does, you can.
Essentially fully charged.
Exactly, yeah. Fully charged, zero current through it, open circuit. And so, VC of 0 is, or you can use a voltage divider to solve for VC of 0 because these voltages are in parallel and those resistors are in series. So you're taking 5 over 6 plus 5. 5/11 of 50 volts. 2.727?
22.7.
Okay. right? That is our first voltage. Yeah, no. All right, see you later. Okay. That is our initial condition. Yeah, 22.72. Now we need to find our VC of infinity for our first equation. So at this point, at t equals 0, switch A is open. However, switch B is still closed. So we're not going to change anything with that. All we're going to do now is remove the 5 ohm resistor because it is now disconnected from the circuit. The switch is open.
What are we doing at t equals 0 or?
Now we're looking for VC of infinity. And that's 6 ohms. And that's 50 volts. And VC of infinity here is what?
I thought it was 0. Wait, my bad.
No. The current through it's 0, but you don't need to know that. 50, yeah. Because it's an open circuit, there's 0 current, therefore 0 voltage across the 6 ohm resistor. So, oh, there we go. Could you go to the lounge and grab like a handful of plates? Thank you. You're the best, Karthik. Okay, yeah, so that's our VC of infinity. And that's what we're going to use in our first equation. What's up?
Is it open? What's open? What's closed for this one again?
So at this point, and let me draw time frames here. This is t less than 0. This is for 0 less than t less than 2.1. However, we are taking it as t approaches infinity. That's why we can draw it as an open circuit.
A is open, B is closed.
And at this point, yes, A is open, B is also open.
Can you just say both are at that point when t equals 0? That's what I said.
Wait, say that again?
Can you just say that the time frame t equals 0? That's what I said
For the first circuit,
for the second circuit.
t equals 0?
Yeah.
What do you mean?
That's what I said. Question I think it's open and closed. T equals 0, switch A open. A is open.
Yes. So this circuit holds for this time frame. That's why I'm writing this time frame. Because at t equals 0, switch A opens, but at t equals 0, it would be wrong to draw this as an open circuit.
But I think for 0 less than t and t greater than 0 less than 2.1, A is open and B is closed.
B is still open. B doesn't close until 2.1 seconds. Yeah. But yeah, so I mean, this is where things get confusing with sequential switching circuits. And I've given this rant or tangent, whatever you want to call it, sidebar, a couple of times before. But essentially, the capacitor is never going to get to the value that we find for VC infinity, which is 50 volts. It's going to get close to it because it changes exponentially. But unless the time constant is significantly less than 2.1 seconds, it's never going to reach that value. But we still have to find it to model the equation of the voltage across the capacitor. We always have to find VC of infinity. The only time we don't find it is when you have one of your edge cases with a current source in series with the capacitor or voltage source in parallel with an inductor. At that point, you do integration in calculus. But that's edge cases. We'll get to that later. That's not what's going on here. Here, you still have to find VC of infinity to model the equation for the voltage across a capacitor at this time frame. And so the last thing we need to do is find tau as seen by these two terminals, which is just 6 ohms. So tau for a capacitor, your time constant is R times C, which is 6 ohms times C, which is 3 farads. So 18 seconds. All right, 18 seconds is your time constant. So that means it's going to take like a full minute almost for this capacitor to fully discharge.
So why do we keep this part at infinity if there's another circuit after the point?
That's where it gets confusing. It's like, yeah, this circuit is only valid for this time frame, right? 0 to 2.1. So why would we need to find the value of the voltage across it at t equals infinity? It's just what you have to do in order to build out this equation that would model the voltage hypothetically if it were to go to infinity. Like hypothetically, without that term, you can't find VC of 2.1. You can't model the voltage at t equals 2.1 without building this equation out fully, even though it's never, like in this actual circuit, it'll never actually reach that point. It's only going to get to 2.1 seconds, and we're about to find what that value would be, what the voltage would reach in that time frame.
Can we say, like for the second, this one, it basically means right before 2.1 seconds, what VC is.
Yes.
Right in that instant before 2.1.
Yes.
And that's what VC infinity is for the first time. And the second time when you do VC infinity is whatever time it is as far as it is possible after 2.1. As long as it takes.
Yes. And right, for after the switching event at 2.1 seconds, there's no more switching events at that point. So the voltage actually will reach the steady state, the VC of infinity, the final value. It will actually get to that point. But regardless, in both cases, you still have to find it. It doesn't matter if it reaches it or not, you still have to find it. Yeah, it cracks. That nature of the equation. Yeah, you have to get that. It's a model. And it's like if you were to graph it, it's like it'll decay to that point at 2.1, and then it's going to start, exponentially growing again or decaying again even more, right? It does. It depends on the circuit itself. Yes. Yeah, and that's what you're dealing with here. I really appreciate it.
I think Val's received.
Okay.
She gets it?
No, not yet. Okay, so let's finish the equation for our first time frame, which is 50 volts plus, and then it's going to be 22.727 minus 50. So it's going to be minus 27.28. How do you know that? 18 seconds. And that's for 0 less than t less than 2.1 seconds. Right? That is Rishabh. What's up, man? Pretty good. Okay, yeah, so that's our first equation. But remember what we're going for here? We're using that first equation to find our initial condition for this equation that we are going to then use to solve for VC at 3 seconds. And at this point, I'm going to try to, get moving a little bit. I know we're all trying to eat, me especially. So I'll try to move through this one a little bit quicker. But stop me for questions if you have any, please. Okay, so now we are going to find VC at 2.1 minus. And if we have VC at 2.1 minus, we have our VC at 2.1 plus, because capacitor voltages cannot change instantaneously. Therefore, we will have what we are looking for, VC at 2.1. And that's going to be 50 minus 27.28 e to the negative 2.1 over 18, which is 25.72 volts. So again, back to what I was saying, right? It's never going to reach 50 volts. It's only going to get to 25. We still have to find it to model the equation.
We plugged in 2.1 to the equation that we just got from the previous step.
You did 50 minus 27.28 e to the power of negative 2.1 over 18? 2.1. Or what, the time constant?
No, we're just.
The 27 comes from this equation, VC of 0 minus VC infinity.
The 2.1, is it milliseconds?
It's seconds. Yeah. Yeah, it comes from 27.72 minus 50. That's where that term comes from. Now, we need to find our new VC of infinity. So at this point, switch B is going to close, and this is our circuit. Resistor. volts. $30, 8ix. Oh crap. 30 volts. Yeah, 3.5, 1.5. 3.5 ohms, 1.5 ohms, 50 volts plus minus VC of infinity, and that is 6 ohms. Okay, and Ix is defined to be the current traveling through this branch. Okay, so this is our circuit. We're looking for the voltage across these terminals. So there is definitely an easier way to do this. Does anyone see it? You can easily solve it using two equations. KVL. Yep, 2 KVLs. It's just one giant loop. So you can write 1 KVL to solve for Ix, and then another KVL either around that loop or around that loop to solve for VC infinity. So let's see what that would look like. Let's take this to be our first KVL. Right, so it's going to be starting from the bottom left, minus 50 volts, because we enter the negative terminal first. And then it's going to be plus Ix times all these resistors in series. So 6 plus 1.5 plus 3.5. And then plus 8Ix minus 30 volts equals 0. Does everyone see where that comes from? Just the KVL, the reason that works is because your dependent source also is dependent on the same current that is in that loop. So it's very convenient, because we can use this equation to solve for Ix and get a number. 4.21 amps. It's just part of the KVL, so I'm doing minus 50 plus Ix times 6 plus Ix times 1.5.
I thought it was a separate equation.
No, it ran out of space, This is all one equation. Okay, so yeah, using that equation, you can solve for Ix to be 4.21 amps. And then you can do a KVL around this loop, and you'll get negative 50 volts plus 6 times Ix plus VC of infinity equals 0. And using that equation, you can solve for VC infinity and get 24.74 volts. Volts. 7.4. And then, yeah, okay, yeah. And then last step is to solve for your Thevenin resistance as seen by the capacitor, right? So we can find our time constant. And since we are working with a dependent source, we are going to have to do test source. So I'm going to short out both of the independent voltage sources, insert a test source where our capacitor used to be, give it the value 1 volt, define a current to be leaving it, IT, and solve for that current. .5 ohms plus minus 8Ix. Redrawing that right. Yep, looks good. And then Ix is this current right here. And yeah, so now we just have to solve for IT. Once again, KVL is going to be a great way to do this. We can just take this loop here and observe that the only variable that would be missing is going to be, or the only unknown variable in that KVL equation on the right loop would be Ix. And so we could use this equation to solve for it. Right, that KVL is going to be negative 1 volt plus Ix times the resistors in series, 1.5 plus 3.5, plus 8Ix is equal to 0. So that's 5. So 13Ix is equal to 1 volt. Ix is equal to 1 over 13 amps. Right? And then using that, we can very easily solve for the main objective here, which is this current right here. We can do that using a KCL. We know the current leaving to the right of IT, and we know the current leaving to the left of IT. Let's call this IY. What would IY be? Exactly. 1 volt divided by 6 ohms. Yes, you could, but it would be kind of like going in circles. You could set a ground here, which leaves you with one more extraordinary node. But you know the value of that voltage is 1 volt, and this is, you'd have to leave this current as a variable. So you'd have minus IT plus 1 volt over 6 ohms plus 1 volt minus 8Ix over 5 ohms. That's valid. That's a valid equation. You would just then need some sort of KVL or maybe another no voltage equation for Ix. You know, for Ix, you could say Ix is equal to 1 volt minus 8Ix over 5 ohms.
Yeah, that's what I'm doing.
If that makes more sense to you, then yeah, go for it, because that's a valid approach as well. So yeah, Iy is equal to 1 over 6 volt, or 1 volt over 6 ohms. Ix is equal to 1 over 13 amps. And so we can say that IT is equal to Ix plus Iy, which is equal to 0.2436. And so R Thevenin is going to be the ratio between our voltage and our current, which is going to be 4.105 ohms. And so our time constant for this equation is R times C, where our C is 3 farads. So our time constant is going to be 12.32 seconds. Almost done with this question. Promise. It's a lot. But any questions at this point? I know a lot of y'all walked in while I was working through this. I'll give more of a formal introduction after this problem while we're eating. But yeah, okay, so that's our time constant. And so now we just need to write our second equation for the voltage across the capacitor after 2.1 seconds. So we're going to take our new VC infinity, 24.74 volts, plus our voltage at 2.1 seconds, which we found to be 25.72 volts, minus our new VC infinity, 24.74, times e to the negative t minus 2.1 seconds over our time constant, 3.2. Right, and then from there, we go back to what the question was looking for. What is VC of t at 3 seconds? So V3 of 3 seconds is going to be 24.74 volts plus, and I'm going to combine the terms in the parentheses to get 0.98 volts, e to the negative 3 minus 2.1 over 12.32. And then that gives us our final answer, 25.65 volts. So after a cool 3 pages of work, I wrote a little big, granted, but we have our answer.